Hi, Professor Gosimi here. In this component of the lecture, we will be discussing the naive Bayes algorithm. Now, one way to think about text is as a sequence of random word generation events. So turning our attention to the right-hand side, for example, we could say that anytime a sentence starts, there's always a first word, and we can call that first word generation event, event A. And we could also say that that first word is followed by another event, called the second word, and for short, we could call it event B. We could also enumerate some of the properties of the first word event and the second word event, such as the kinds of things that could happen. If you're a first word, you can be, let's say, the, a, in, or but. And if you're a second word event, you can be cat, dog, if, and you. Now, once we've gone about describing the world this way, we might be interested in making some estimates about the probability of the event A and the event B. And usually, if we wanted to do that, we would take some training data. So for example, let's say we had the very simple training data set that I've shown on the bottom there. The cat, the dog, but if, but you, and the cat. Well, we could use this training data to generate some probabilities for the events. For example, I could come here and count up for the first words, how many times did the show up? And I can see here that the shows up 3 out of the 5 times in the training data as the first word. So I could assign the a probability, or a prior probability of 60%. Now, similarly, I could do this for the second words. I could come and say, out of these 5 sentences, I look at the second words in each of those sentences. How many times does cat show up? And cat shows up 2 out of 5 times, or 40%. Now I could repeat this process using the training data and come up with, for event A, which is the first word, and event B, which is the second word, something that describes the probability of each term in the vocabulary being generated. Okay, well, once I have this generated, I could start asking questions like, if I wanted to in the future know what to expect about the probability for a new event, a brand new sentence I've never seen before being starting with the word the, I would know 60%. Or I might be interested in knowing what the probability for a brand new sentence I've never seen having a second word being cat. I could also estimate that using this very simple data set that I've compiled and represented this way. Now, of course, I might want to do something more sophisticated than just thinking about the probability of the first word or the second word. I might be interested in joint probabilities, like what's the probability of the first word being the and the second word being cat. And if I were pretty naive or I didn't know much about the generative process of language, one thing I might assume is, well, hey, the probability of the word the is 60%, and the probability of the word cat is 40%. So I can just, to compute the probability of A and B, I can just multiply those two together and get this final value of, hey, there's a 24% chance that the first word is going to be the, and the second word is going to be cat. But that is naive, right? Because in reality, the second word's value probably depends very strongly on the first word's value. That is, the probability of A and B, is not just the probability of A times the probability of B, but it depends on the probability of A times the probability of B given whatever the word A was. And if we kind of turn our attention back to the training set, we can see an example of what makes those two different. Let's say that the first word in the sentence was the. Okay, well, if we're interested in only the universe of sentences right now, where the first word was the, we're going to eliminate the sentence that starts with but if, and the other sentence that starts with you, but you. Now, among this universe of sentences that start with the word the, I could ask, what's the probability in this universe of seeing the second word as cat? And you'd see here that the probability is 66.6%. 0.7 as opposed to the 40% that we saw when it was not a conditional probability. And of course, you could do this for all the other terms in the dictionary if you were interested in computing the conditional probabilities. And furthermore, this process could be applied not only if you wanted to estimate the probability of the second word given the first word, you could also do it for the probability of the first word given that you knew the second word. So let's say I knew that the second word in a sentence was cat, and I was interested in figuring out the probability of the first word given that knowledge. Well, again, if I come back here to my training set, what I would notice is that that conditional probability is actually 100% because there's no example in the training data set where I ever see the word the not preceding the word cat. And so I would assign 100% probability to that location. And I could do that for all the other terms as well in this case. Let's say I combine those two observations that we saw in the previous two examples, that probability of B given A was not the same as probability of A given B, but I wanted to find a way of coming up with a relationship between those two. Well, I would know that probability of A and B is the same as probability of B and A, and so I can compute those two separately, do a little bit of algebra, and come up with a rule that's called Bayes' rule. And really all Bayes' rule is trying to help you understand is the relationship between the conditional probability between events in one direction and the conditional probability in the other direction. So given that I knew something about the probability of word 2 given word 1, what would that tell me about the probability of word 1 given word 2? Is effectively what you're trying to figure out. Now, in any kind of Bayesian statistics or statistics in general, if, let's say, we're interested in finding the probability of A given B, this first term, B given A, is what we refer to as the likelihood. The probability of A is referred to as the prior, and the probability of B on the denominator is referred to as evidence. Okay, well, we can use this property of Bayes' rule to generate models that are computing difficult to measure things using easy to measure things, such as sentence sentiment, right? Okay, so let's consider the following example. Let's say I want to know the class of some sentimental value of a sentence given some data about it. So let's say this data is represented by W, and W is a vector that contains a representation of the sentence, I am not feeling happy. Okay, well, I might be interested in saying, what is the probability that the person's happy, given that they provided the data? Or I could write that more succinctly so that we save space. What's the probability of C given W? And as we just saw in the previous example, we can relate or describe the probability of C given W as the prior, which is the probability of C, the likelihood, the probability of W given C, and the evidence, which is the probability of W. Now, one thing you should note here is that the probability of W, or those words there and how they kind of relate to each other in a joint sense, has nothing to do with C. And so if I were trying to compare the probabilities of happy, sad, or neutral, that effect from probability of W would be constant in all three cases. And so for that reason, if we're interested in performing classification by saying which of these three events is more likely, for example, given the model, we can actually just toss that term out. There's no need to compute it. And so that is to say that the probability of C given W is proportional to the probability of C, which is the prior, and times the probability of W given C, which is the likelihood. Now, when we talk about a prior probability of C, that just says how likely is it that this outcome that I'm interested in predicting is going to occur. Conventionally, the way that you go about deciding that is by using your training data. So I might, for example, have some data that tells me in the whole universe of sentences, 20% of all of them tend to be happy. So knowing absolutely nothing else, I have a 20% guess that the sentence is happy. Now, I should also note about priors that you don't have to use the training data. You could reflect something about an expert's opinion in those priors or some special knowledge that you have about the situation to estimate what you think the likelihood is of the class with no additional data kind of being taken into account. Okay, and so in this case, just to be very clear, if we were interested in the probability of happy given the words, and we used the values that are shown there on the right-hand side, we would know it's proportional to 0.2 times the probability of W given happy, which again is the likelihood. Okay, so if we want to go ahead and compute this whole equation so that we can finally get to the probability of this sentence being a happy one, all we need to do is figure out how we compute that likelihood. Well, you can recall from the very simple example that we did with word 1 and word 2 that you can expand out this probability in the following way. You can say, well, okay, if I want to know the probability of W given the word happy, I have to first figure out what's the probability of W1, this term here, given that I'm happy. And then I have to figure out, given both that I'm happy and that my first word was W1, what's the probability of W2 coming next? And then I have to say, okay, now, given that I'm happy and my first word was W1 and my second word was W2, what's the probability of me creating W3 as the next word? And so on and so forth. And what this equation here shows is exactly that thought process, right? This is a valid way. In fact, it's the correct way if you really wanted to get at the probability of W given happy. However, there are some real-world constraints that could make the computation of probability of W given happy very challenging. Consider, for example, if you don't have a lot of data and you want to do this classification. Well, for each additional axis, or in this case, word that you're adding to your W vector, the space is growing exponentially, and therefore the sparsity of that space for a given amount of data is going to grow exponentially with it. So oftentimes, because of how unwieldy these very large conditional probability statements can get, people will make some simplifying, albeit naive assumptions to make their lives easier. Such as, for example, assuming that the value of one word has no bearing at all on the other. So whatever W2 happens to be has nothing to do with W1, W3 has nothing to do with W2 or W1, and so on. And so effectively, they just throw these out and make that naive assumption so that the probability of W given happy is simply the probability of the first word given that you're happy, the probability of the second word given that you're happy, the probability of the third word given that you're happy, and so on, which is significantly easier and more computationally tractable and is not as sensitive to issues like sparsity in your data set. Of course, this assumption that effectively the words are independent is technically not correct. Of course, making this simplifying assumption helps with the computational side of things, but at the cost of the performance of your classification model. So this method that we just discussed of estimating a class probability given the features while making the simplifying assumption about the independence of the features is what's referred to as naive Bayes.